So welcome to an introduction to testing, which probably is about the worst, the lamest title that I've heard so far today in the OPSI talks, and I should have been much more creative. I even thought about different title slides. This one probably should. This one I think maybe is a little bit better than the old-fashioned computer. But anyway, my name is Dave Oswald, and I work for Bluehost Endurance International Group. I live in Salt Lake City and I work in Orem, Utah. I want to thank Endurance for letting me be here for a week. I came on Saturday and spent Sunday setting up for the conference, and I'll be here through Friday and then vacation after that for another week. So thanks to Endurance. And also I want to thank everybody in this room and the Perl community at large for making the Perl conference possible and making our careers possible. I'm very much happy to be a part of all of this. And I've done this in previous talks. I want to thank my family also for being without me for a week. They're probably thanking me for going. Okay, so today's goals really are to learn how to write testable code and how to write unit tests. And if you've already written tons of unit tests and are testing everything quite well, then this probably is not the talk for you. We're not going to get into deep issues of how to test the untestable and things like that. We're going to talk about how to think with a test mentality and how to write simple tests. So if that's where you want to be, then we're in the right room. This is kind of like the first day of class at the university where the professor says, now this is writing 101, and if you expect it to be in math 302, this is the wrong room, and somebody always gets up and sneaks out. So this is your opportunity. Or at any point throughout, no hard feelings. What was it? So we're going to explore test more, and we're going to learn how to prove our code. But also, I like to kind of have fun when I'm talking. I do these things because I enjoy them and have fun preparing them and also have fun giving them. So let's try to enjoy ourselves a little bit today, but not too much fun. We won't have to. Okay, so some resources that I consider valuable in learning about testing are the books Intermediate Perl, the book Modern Perl. The book Perl Testing, a Developer's Notebook by Chromatic is a very good resource, and even the documentation for Test More, the module, are all good resources. I think I was at a point about 10 years ago where I kept hearing people talking about writing tests, and I had this vague concept of what that really meant, but I hadn't really deeply explored how that works, and making that mental leap from I'm writing this software to how do I write tests to make software work. It was something that was a little bit foreign to me a while back, but once I had read through some of these materials, it really all came together for me, and so they're good resources. So what is unit testing? For every unit of code, we're going to write code that invokes that code and verifies that the result is what we expect. We test as many edge cases and logic paths as we possibly can when writing unit tests, or at least we should. This also means that we have to write code that is testable. I want to give an example of, in Perl, kind of how a hierarchy of files might work that we would test. We might have a bin folder with some sort of a script in it that runs. We might have a lib folder with a module that we would like to test, and then we'll have a T folder with various programs in it that we're going to run, various scripts that we're going to run our tests. So sometimes a little visual up front kind of helps. So we'll get to a point where our little test scripts here are going to run and test out our library, our target. There's no introductory to testing that could be given without talking about test-driven development. I'm sure everybody here already practices test-driven development. Is that the case? No. You do, okay. You do, good, great. You guys shouldn't be in here, I'm just kidding. Test-driven development it starts with the concept that all code is guilty until proven innocent. I like the modulicious take on it, which is it's not a feature until there's tests, and a patch is not accepted until there are tests in support of the patch. You know, a new method is not part of modulicious until there's a test testing that method. So, The way test-driven development works is that initially you write tests that fail, and then you write enough code to make the tests pass. And once the tests pass, then you refactor your code to give it to improve its code quality. And then you repeat the process. So you do this in small chunks, small segments. Some of the things that I work on are relatively complex and have some terrible type coupling. And so for me, many times the only opportunity that I have to ever even actually touch the code that I'm writing is to write tests that can go through a whole behind-the-scenes setup process. And so really writing tests for me is very much a part of being able to make any progress in what I'm working on. So to reiterate the steps, we're going to write tests that will fail because the code doesn't yet exist. That's test-driven development. Then we will write the simplest code practical. However, a little foresight is sometimes useful. For example, if we know in our test that we're looking for 2 because we were writing a method called add11, it doesn't do any good to actually write a method that just returns 2. Right? A little foresight is useful in the code we write to pass our tests. And then finally, we're going to verify that the test now passes. And if it does pass, then we'll run another test, and then more code to support that, and if not, then we'll fix the code. And then we can refactor and improve the functionality, improve the elegancy, whatever it is that we want to do in refactoring the code. One point that I like to make is that testing gives us the power to refactor. A lot of times if there are no tests in place, you're afraid to even touch the code that you've written because how can you ever prove that it's going to do what you expect it to do a second time? It worked the first time. You almost feel like you maybe have to replicate bug for bug everything that you've done in your original iteration. With tests in place, you have the freedom to refactor. So, test-driven development is a trade-off. It's the slower way to arrive at hello world, so to speak. It's maybe a slower way to arrive at our goal, but it's the faster way to develop non-trivial solutions, I believe. Bugs are spotted and fixed as they occur, we hope. And unit tests empower us to make changes. Test-driven development leaves us with both code and, in a way, regression tests already in place. One thing that I should mention when I say bugs are spotted and fixed as they occur, that is only in as much as the developer himself or myself doesn't have our blinders on. So we always have a certain set of blinders on as we're writing code. We write tests because we expect, well, this is an assertion that we're making in the code that we're writing, but we may not be thinking of everything. And so I'm writing my tests, I'm writing my code. What about the things I didn't think about? Well, so writing tests up front is very helpful in making assertions that the code is working as I expect, but it may not be all that helpful in making sure that the code is working as everybody else would expect as well. So testing is easiest to accomplish when we're testing in small chunks, when we're writing small chunks of testable code. If you write the Windows operating system and then try to write the tests to test the front end of it, that's very hard, right? If you write small chunks of code and test those small chunks, that's very easy to do. So we test and code in small chunks. One nice thing about writing our tests as we're writing our code is that it forces us to think in these smaller chunks. And it tends to lead us to more generally useful solutions and to having simpler and easier to reason about code. Code in small units of functionality, they're easier to reason about, easier to test than heaps of steaming spaghetti. Factor complexity into smaller subroutines so they can be tested in isolation. And decouple logic from tricky integrations. So a word about modular design. Non-trivial applications should put as much work as possible into separate modules. So if you're writing a cron, and it's a non-trivial cron, it has to run on a system, rather than putting all of the code in the application file, in the cron file itself, in the cron script itself, write a module that handles your business logic, and then your cron script can be a simple wrapper around that module. And that enables you to test. It's much easier to test the module than the runnable script itself. So, in this example that I have here, the main application might be use my module do it, and then call do it, and then die if we don't get success. And that might be our simple script. But we're not going to, and we really have a little bit of a hard time testing that. It's much easier to test the code in my module, and we'll see that in just a minute. So why do we want to write in small chunks of functionality and test it? Well, a flight recorder is a great example of a black box. It receives information in, and upon request gives us information out, and it's heavily well tested, and we expect that it's going to work, and we know that it's going to work. Another example that's a great example to me of modularity is the Mars Rover, where I presume, I don't work for NASA, but I presume that every component of this was tested individually. They have probably statistics on how well the wheels are going to wear, the tires are going to wear. They know how the camera's going to work and how the arms are going to work. And each of those units of functionality are tested in isolation before the great integration takes place of putting together the rover and launching it. Because it's just easier to test modular code, and it's harder to test a great ball of spaghetti or rubber bands or whatever. In the real world, unfortunately, we're presented with the great ball of rubber bands. Most of the code that I look at is so tightly coupled and hard to test. But as we're working, we should maybe strive to improve that situation. So we're going to look again at the simple test framework. We have an application directory. And in that application directory, we have, for example, an application itself, app.pl. And then we're going to have a couple of libraries, libmymodule and lib some other thing. Doesn't matter. Excuse me. And then in the T directory, we're going to go ahead and put our test scripts that are going to execute the code that that tests our modules. So here's an example of a simple application. Our simple application uses find_bin to know where the library is, and it uses strictum warnings, and it uses the modules, and then the main application code that we saw before, similar to. And again, we're showing that we want to put most of the business logic and most of the difficult stuff we want to test into our modules. In practice, it's hard to boil the entire runtime down to a module with dependencies, but as we strive to shift as much business logic as possible and keep package main as simple as possible, it makes it easier to test the code. And the payoff is small subroutines being easy to test and separate modules facilitate this testing. So our examples are going to differ a little bit from what I've just explained. We're going to go ahead and throw the code that we're testing right into our test scripts in our examples here, because it makes it easier for me to show on one screen. Some of the basic tools for testing are test more. Is everybody here to use test more? Has anybody used it? Some people? Okay, good. Test harness, which executes our test suites and consumes tap. Let's discuss what tap is. Test more is a framework that produces output as it runs our tests. And the output that it produces is a bunch of OKs or not OKs. And we call that tap output. And it's a regular output that can be easily parsed. And test harness parses that tap output. Tap stands for test anything protocol. Test harness processes that tap output and produces a summary of pass and fail for our test suite. And to run the test harness, we use an application called prove. And it's provided by test harness, and it basically runs our test suite for us. So let's look at a simple set of tests. In this example, we're using test more, and we've implemented the function divide. We pass into divide a dividend in the divisor, and we return the dividend divided by the divisor. So as you can see, it's very complex code. And then we're going to go ahead and test this code. And we test it by simply asking questions. Is it okay to assert that dividing 4 by 2 equals 2? And then we give our test a name. Even positive integers, we call this test. Then we ask, is it okay to divide -3 by 3 and get a -1? Does that assertion come out okay? So on the left you can see we have, mouse one. On the left here we have a Boolean assertion, and if that Boolean assertion is true, then our OK method is going to produce output that means that is true. And here we're testing floating point, for example. So now I've created a divide function, and I've said, well, what are maybe the edge cases that I should check out in my division function? Well, I want to make sure that even positive integers can be divided correctly. I want to see if a negative and a positive comes out correctly, because as we know, you have to kind of give that consideration when you're doing longhand division. And I want to see if 2 negatives come out correctly. That's another edge case, perhaps. And then I want to see if floating point is handled correctly. And so here I've gone ahead and tested several assertions, and those are assertions based on my kind of knowledge of the problem domain of division. Assertions that I know must be true if my division is working. When I run those tests, when I run that test suite on the left, it's going to produce this output on the right. OK 1, even positive integers. OK 2, OK 3, OK 4, and then it's going to tell me that it ran tests 1 through 4. Now, let's change our tests a little bit. We're going to say that dividing -6 by -1 equals 5, which isn't right. We changed one of our tests a little bit. And now you can see what fail looks like. OK 1, OK 2, not OK 3, 2 negatives. That test failed, and it tells me which line within my test script failed, so that I can find it easily. And this is why it is also useful to give unique names to our tests, because I can easily look and see, oh, not OK, 2 negatives, and I can look at my code on the left there and find out which of the tests it was that failed. So now I might ask myself, well, what should happen when we divide by 0? And I might decide, well, if we divide by 0, then we should not get back a defined number. We should get back undef, is what I'm going to assert in this particular test. And so I've now modified my function to return undef if the divisor is equal to 0. And now we'll run our tests. Or maybe we can decide that the right thing to do is what everybody else does, which is to throw an exception. When we run the tests, we'll get OK 1 divided by 0. There's 2 ways to run the tests. One, you can run Perl and then execute your test script. Or you can use proof, and proof produces the tap output, which includes the pass and fail at the bottom. So let's look at another way to test for exceptions. Here we're looking for a return value, and we're evaluating divide 5, 0. If val is going to trap any exceptions, and then down at the bottom, we have, okay, the exception is like this regular expression. So now by using like, we're comparing the exception that we got when this threw an exception with the pattern, the regular expression pattern, illegal division. And when we run that, then we get OK 2 exception is illegal division. So, any questions so far? We're going to come back and hit all of the different functions next. Okay. So the first function, the first test function that you saw me use was one called OK. And to OK, you pass an expression and a name. And the expression is evaluated for Boolean truth. And if it gets back Boolean truth, then your test passes. Okay, successful. And if it evaluates to Boolean false, then your test fails. Okay, not okay, the test failed. So there are a few more functions provided by test more. Is, isn't, compare okay, like, unlike, is deeply, and a few others. And I want to look at each of those. So first, let's look at strings. Here I have a subroutine that alphabetizes the characters in a string. Alphabetizes in ASCII order, I should say. Now I'm going to test is, I'm going to make my function call alphabetize ASDF. Is the response that I get back from that subroutine ADFS, which is the alphabetical order? And if it is, then my test will pass. And sure enough, when I run it, I get OK1, alphabetized ASDF. So the way that you call each of these commonly used subroutines in test more, OK gets a Boolean expression and a name, is gets a target string and a wanted string. Or I guess we could say the string that we're testing against the control string, against the wanted string. Isn't gives us the string that we want, or the string that we are testing, and makes sure that it is not the same as the string that we don't want to get. Like tests our string against a regular expression. Unlike tests that our string does not match a regular expression. And CMP OK, compare OK. I'm not supposed to walk around because then I go off camera, but I guess I'll just point with my mouse. CMP OK, we test the return from whatever it is that we're testing against something that we want, and then we can provide a relational operator in here, less than, greater than, equal to, not equal to. And then the final one here, is deeply, is nice because it allows us to take an entire data structure and test it against a wanted data structure, deeply, recursively. And we'll look at that in just a minute too. So we've already seen this one, okay. On the left we have 1 plus 1 equals 2. This code is actually going to run when we run our test. It's going to test 1 plus 1 to see if it is equal to 2. And if it is, then it'll print OK. With is, we're going to test a string against another string. With isn't, again, we're going to test a string against another string. With like, we're going to test a string against a regular expression. Unlike, again, a string against a regular expression. With compare, OK, we test the thing on the left with the thing on the right using the operator that we have in quotes in the middle. So, on the left, we're going to compare 1 with 2 numerically. Here we're going to compare Dave with my brother Dan using greater than, and that'll be ascibetical comparison, a stringwise comparison. This one is a lot of fun. Is deeply. With is deeply, at the top up here, we're creating a structure. The structure contains an array ref. The first element of the array ref is a number. The second element of the array ref is another reference to an array that contains 2 elements. And then the next element is another array ref that contains 2 elements, and then finally 1 element. And we're going to say, is my structure here equal to this structure? And if so, then we're OK, and the structures match recursively. So where is that useful? To me, it's useful when testing, for example, JSON decodes, or when testing objects' internal attributes, an object's internal state. Okay, here's an example of using is deeply. So my structure, 1, 2, 3, 4, 5, and 6 is deeply, and when we run it, it says the structures match recursively. And one of the reasons that is deeply is so useful is that When it fails, it tells you right where it failed. So here we've asked if the 4 and the 5, I better point with my mouse, can you see this? The 4 and the 5 here, I'm testing to see if those actually are 5 and 4, which they are not. So that's going to fail. When it fails, it tells us that the structures began differing at this point, and that we got a 4 when we expected a 5. So that's, to me, immensely useful. This is also why we use is instead of okay, because when is fails, it tells you I expected the thing on the left, I got some other thing, what I wanted was the thing on the right. It tells you, when is fails, it tells you why it failed. When okay fails, all that it can tell you is that it got Boolean false. Okay, so now for a modular approach at testing, we're going to create a module called package-my-module, and it's going to use exporter, and it's going to export a method called, or a function called add, and add just returns its two parameters added together. And now we're going to write tests for our module. And we're going to put them in a script called t/00myModule_t, and we're going to use test more. Over there. We're going to use test more, and we're going to use something that test more provides us called use OK. Anybody know what use OK does? Yeah, go ahead.
Just to check whether you loaded your module.
That's right. Use OK essentially wraps use module name, the Perl directive to use. It wraps it in probably in a val, right? And if it fails, then it produces useful output with the tap parser confined. So it tests to see if the module loads. And then the next thing we're testing, can OK. So can my module add? Does my module have a method, have a subroutine named add? Now my module is also, as we saw before, is an exporter, and it exports the method add into the caller's namespace. So we're going to do another can test. Can main add? In other words, did the module export its function as we expected it to? And if so, now we can do OK, add 1, 1 equals 2, and our two positive integers being added together worked. And then when we're done, we write done testing. When we run that, if we run it with Perl-ilib and then this test script name, then it'll tell us, OK, 1, use my module, succeeded. So use OK, succeeded. OK, 2, my module can this. OK, 3, my module can that. Oh, and I guess I added a fourth test that didn't make it onto this slide. Thanks, sorry about that. Anyway, if we use proof, we're going to tell it proof-l, and I'll explain what that means in a moment. And then it'll tell us that the tests in this particular test script, my module, .t, all passed, all tests successful. One file ran, it had 3 tests in it. It took a certain number of wall clock seconds and all, and then in the end, we got a big pass at the end down there. Success. Anybody know what the I flag does on Perl-I? Yes?
It adds that directory to the path that Perl
Is looking at. That's correct. So let me see if I don't have my, I can show you here. Maybe. All right. So in this example, we are in the directory testing 1, which has no significance as a meaning or anything. Our module that we're testing resides in lib/foo, and our tests reside in t. And so if I were to run tests from this path, I could say Perl-I lib, and it would look for the module that I'm running in the lib directory. That's all that it's telling me. On the right side, we have proof, and proof is using -l, which does the same thing as ilib. It's just a shorthand for ilib. Okay. So in testing that little module, we used use OK, we used can OK, and we used proof to run the entire test suite. Proof, it turns out, has more command line switches than just -L. It also has -V, which I find very useful. That produces verbose output. When you use -V, it will show you the output of every single test within your test script, whereas without -V, prove only shows, yes, my entire script passed or failed. If there is a failure, then it will still dump which test failed, even if you're not using -V. Proof -B is useful for CPAN module authors because it tells Perl to look in the blib directory, which is created when you run make as you're developing your CPAN module. Proof-L is common for people that are not developing for CPAN or that aren't using make. It just tells Perl to look in the lib that falls within your current working directory. And proof-Q is used by tools such as CPAN- to suppress all output except for failures and to produce only summary output. Are there any questions so far? Yes.
Did you explain what the fine bin was?
Defined?
The fine bin?
Oh, fine bin. Oh yeah, let's go talk about that for a second. All right, this is a module that comes in with core Perl. So the question is, what does fine bin do? This is a module that comes with core Perl. It ships with every version of Perl, unless it's a broken version. And fine bin can be provides certain variables that tell me where the actual executable script that I'm running resides, where it lives. And so, if I happen to know that my libraries for a particular script run or live within the script's working directory /lib, then I might tell Perl to go ahead and use the library that can be found where my bin is, but back up one, and then move forward into lib. So, assuming that I have this directory structure where greeter lives in bin, then I'm going to walk over here. Sorry, I'm going to go off camera for a second. Greeter lives within bin. Find bin tells Perl that it should look at greeter here, back up one, move forward, and then move forward into the lib directory to find the library. So let's look at that again. Find bin is using a variable called find bin. That represents, over here, the bin directory. Find bin is where my script is living. And then the dot tells it back up one directory, and then the lib tells it move forward one into lib. So it's basically a way of telling Perl where to find the libraries for a particular script that's running. Yeah, as long as I know relative to where the script lives, where the libraries are going to be, I can go ahead and put that in there, and Perl will never have a hard time finding the libraries that this script relies upon. So then we run the tests. Okay, so the tools that we used were useOK, which loads the module and sees if the module can load without failing, canOK, and proof. UseOK, it turns out to be more useful than it really ought to be. In a perfect world, I would never forget to run Perl-C to test if my module compiles before running my tests. But in the real world, I forget to do that all the time. Or I forget to put the 1 at the end of my module to make the module return a true value. There's always something that I'm forgetting. So if I put useOK in my test script, then I automatically, immediately am able to determine that my module that I'm trying to test failed to load, and that there's a syntax error in it somewhere, or a strict violation or something. And then we looked at the proof command line switches. Now we'll look at subtests. So when I'm writing tests, I try to be very simple in the way I write my tests. I don't like to get too clever. If I'm testing 6 different things, I will write 6 different tests, even if the tests look quite similar to each other. I don't try to get too complicated. I don't try to run things in loops. I want my tests to be very easy to look at and reason about. So one way to make your tests easier to look at and reason about is to subdivide your tests into smaller subtests. And TestMore provides this ability with a method called subtest. subtest, the test name, multiplication, is a subroutine, and inside of that subroutine, it has two actual tests that are being run. And then when the subroutine is done with its two little tests, it calls done testing. And now here we are outside of our subroutine, we have some additional tests up here before and down here below. When we run the test script, the first test runs and gives us OK1, and then the second test runs, which is the subtest, and that gives us OK1 and OK2, these two OKs. And then we get a summary here. Our subtest multiplication was all okay. Everything that happened inside this subroutine was okay. Now we'll go on to our third test down here. So the first one up here counts as one test. The second subroutine here counts as one test that has two subtests within it, 1 and 2. And then this one counts as our third test. So subtests provide us a means simply of breaking our tests down into smaller components that test individual, maybe units of functionality. Any questions on subtests? Yes?
Is the indentation correct?
Yes. Yeah.
I would think the subtest it would be under its own indentation.
So actually it is. I'm going to walk over again. So this is the first test up here. These two are subtests, but these all roll up to be one top level test. So that's why that one is outdented again. Does that make sense? Yeah. Some other useful tools: Diag, Note, and Explain. Has anybody used any of these? You have. Okay. So let's start with Note. Well, maybe we shouldn't, because my description is same as Diag. Let's start with Diag. Okay. Diag prints a diagnostic message that won't interfere with tap output. So it's a little bit difficult to print something within your test scripts if it's going to be consumed by a tap parser, because anything you print gets the tap parser is going to try to consume that, going to try to parse it. If you don't want something to get parsed by the tap parser, then you'll precede your output with a pound sign. Using Diag does that for you automatically. So it prints a diagnostic message that won't interfere with test output. So the messages have a pound sign appended to them. Note is the same as Diag, but it is only seen if the tests are run with a -V for verbose mode. So you should probably tend to favor Note if you need your test to spew some output of some sort. Favor Note, unless there's some critical information that you need to get out, even if you're not in verbose mode, and then use Diag for critical information that you want to have print even in non-verbose mode. Explain is wonderful. Explain is like putting a note around data dumper, essentially. So it will dump your data structure, no matter how many levels of complexity your data structure has, but it will put all of the output following pound signs, so it won't interfere with your tap output. I find that tremendously useful because as soon as it deeply fails, the next thing I want to do is explain my data structure to find out why it failed, and so I use explain a lot. So here's some examples. If we call Diag 1 plus 1 equals comma 1 plus 1, then that's going to print pound sign 1 plus 1 equals 2. If I put Note, then it's going to print the same thing, but only in verbose mode. Any questions on those ones? It's very useful for your test to have kind of comments that spew out from time to time. They help me to keep track of where I am in the runtime of the script or what things may have been set up and torn down as my scripts are running. Okay, skip. If I have a test that should only be run on Windows or should only be run on Linux, then I might put in a skip block. And I can make my skip block skip if a condition is true. And if the condition is true, then the following two tests, OK1 and OK2, are going to just be skipped altogether. So if you're on, if this doesn't make any sense on BSD, but it does make sense on GNU Linux, then you would put in a condition, a skip condition, and see where it says because there, that because will spew into the tap output. It will say skipping two tests because whatever you put in place of the actual word because there. Right? That's like the insert your name, right? Insert something into the because. So I would say skip, and then I would put in there, can't run these tests on Windows, comma, 3 tests, and then if the condition is that we're running under Windows. OK1 and OK2, and the tap output would say skipping 2 tests, skipping 3 tests, can't run these tests on Windows. So that's skip blocks. On the right here, we're going to talk about to do for a second. If I want to write tests for a feature that hasn't yet been implemented, then I would mark it with a to do, and I would set the local variable to do equal to some description of why we can't run this, and then a condition. So if this particular condition is met, you could just say if one. You don't even need the if. You could make it just local to do always, because we know that this one's never going to pass currently. In that case, if the following tests in this block of code here pass, then we get a failure because we were not expecting them to pass. We get a big note that says, warning, these tests that you weren't expecting to pass suddenly passed, right? So now it becomes illegal for those tests to pass, or unexpected, and it gives us, proof gives us big yellow output on our screen telling us, warning, those shouldn't have passed, and they did pass. But it's also a great reminder for me as I'm running my tests, oh, there was that feature I planned on implementing, and let's go ahead and implement that now. I've got a little bit of free time, and then make sure to take those out of to-do status and run my tests, and I've already got the tests in place. Good. So, tests that aren't, skip can be used for tests that aren't applicable in a given environment, or tests that should only run for a particular user, tests that are only related to releasing code, tests that can only run if you have a database available to you, or if you have network connectivity. To do is for tests that fail that are awaiting bug fixes, or tests for code that isn't yet implemented, or tests that should arouse suspicion if they unexpectedly pass. Any questions so far? Yes?
What would happen if you skip outside the block labeled with skip? I mean, does that even make sense?
So yeah, if you use skip as a top level thing instead of inside of a block, skip has lexical scoping. So it would be scoped to it has lexical scoping from the point that it's used onward. So everything that comes after that would be skipped automatically. And in fact, that is quite common in release tests or developer tests for CPAN modules. As an example, I might want to, as a CPAN developer, write a test that verifies that my pod, my plain old documentation, documents all of the functions in my module. But I might not want that test to run on every single user's system that's installing my module. And so I will set an environment variable, release_testing, and then I will test. If and release testing exists, then we'll go ahead and run. And if not, then we'll skip them all. And I'll go ahead and skip all my tests at that point. Okay, so in summary, testing saves you a lot of time. And that's something that you might have to sell to your managers, right? Fortunately, I work in an environment where they 100% support testing, and unfortunately don't 100% do it. But it's very easy for me to tell my boss, this is going to take me 3 days, and one of those days is going to be spent writing tests before I even get started, and half the time is going to be spent writing tests as I'm writing the code. And he's totally okay with that, because he knows that he's not going to have to revisit my story again once I've turned it in. You know, once I've submitted my code, hopefully if I've thought of all the potential problems, then the code's just going to work, and they're okay with taking the time to write tests. So it might take a little convincing to sell someone that it's going to take me an extra day to develop this, but in the long run, it's going to save them weeks and weeks of debugging. Tests are easier if you write modular code, small units of functionality. As you saw in the test examples that we have here, it's very easy to test a subroutine. It's very hard to test a grand integration, a big giant thing, a big ball of yarn. Test every logic path that you possibly can. Test the small parts, then the bigger parts that use the small parts. So this is something that we do a lot, is I'll write a lot of little units of functionality, and I'll write tests for all of those. And then later on, I'll write code that uses those little units of functionality, and I'll write tests for the bigger part of the code. And I know that if I get a failure, it's not in the little things, it's in the big integration, because I've already tested all the little things. So kind of work your way up incrementally from the low-level stuff up to the higher-level stuff, testing as you go. Test edge cases, test fence posts, test every assumption that you're making. As we write code, we're constantly making assumptions, aren't we? I assume that as I add this to this, I'm going to get the sum of those two things. Well, test that assumption. Write tests for every assumption that you make. Test the edge cases, the fence posts, the outliers. What happens if I'm adding two integers and one of the integers happens to be the maximum integer for my platform? Test that sort of thing. And of course, test the normal things, the expected behaviors under expected operating conditions. So now, in the last couple minutes that we have, let's find some bugs. We have sub by CSV, and this is a CSV parser. And it's a really smart one. It splits on commas, comma-separated value parser. Okay? And we're going to write some tests for it. We're going to test that can it parse A, comma, B, comma, C into 3 separate elements. That's a simple list. Can it parse a single element into a single field? Can it parse strings and numbers together that are comma separated? Yes. And here's the last one, can it parse quoted constructs correctly? Well, let's see what happens. We run it, and so far so good. But then somebody calls in a bug report and says it returns a number of fields rather than the fields themselves. What? Someone reports that quotes fail to escape embedded commas. So those are 2 strange bug reports. Let's add some tests to see what those are all about. So we add, is scalar by CSV, so we're going to put it in scalar context. Is it A? And then is deeply, John, comma, Doe, as a single field, comma, 79. Does that parse out to be a single field, John Doe, and another field, 79, which is what we would hope that it would do. And we run the tests. Oh, sure enough, that bug report was correct. We got some failures here. We got a failure that we expected A and got a 1. And later we got a failure here that we expected Doe, comma, John, and instead we just got Doe. So whenever I get a bug report from somebody, I like to write tests around that report. At work, when somebody tells me such and such stopped working, the first thing I think is, how can I write a test to isolate that explanation that they gave me? So here's a nice bug report. We've discovered such and such. The second problem is that, and attached is a set of tests. Who's ever gotten a bug report that includes tests? And you have. Perfect. You live in a great world. Usually the bug report is, support said that when they had a customer that did such and such, everything blew up. And then you really have to do some more digging and investigating. If you're ever submitting a bug report for a CPAN module, try to write some tests. It's a good opportunity to have a little fun writing some tests. Try to prove the assertion that you're making that there is a bug. And even better if you attach a patch that fixes the bug. Who's ever gotten a patch? I've gotten a couple, but not many. In fact, Tastic, in this case, if the patch uses text CSV rather than roll your own text CSV. Okay, so summary of the tools. Test More is a TAP producing framework. CPAN has hundreds of other testing tools available that work with Test More. I like to explore CPAN distributions. Prove runs all of your tests. On CPAN, explore the test namespace, the test : namespace. You'll find things like test exception, test warnings, test core, which tests to see if all of your dependencies come from core. Test Deep, which is another way of doing recursive data structure testing that lets you pull out little parts of the data structure and test them. And finally, I'll just leave you with some resources. Again, intermediate Perl, modern Perl, Perl testing, a developer's notebook, the documentation for proof, all those. That's what I've got. Thank you. Thanks.